Hello my friends, and welcome again to my video channel. Today in part 8, yes it is really part 8, we will focus on the topic. In the PLL loop we found a bad 703 differential amplifier, and I got some donations from two nice guys. One, also Stefan, thank you very much, sent me an LM703. And another guy, Elmar, who lives here in my town in Munich, told me that he has 3 of these ICs spare. They have been already mounted in a board. They were soldered, unsoldered, but he thought they should be okay. He checked them with an ohm meter. So I have now totally 4. And I do a little measurement and a test with them before I choose which unit I use. So first, let's talk about the test setup. Here we have the simple test setup. It's only the DC biasing, not more. DC supply and measuring of the bias voltages, input, output, and the voltage drop across the 100 ohm resistors. The circuit is as follows. We can see here the input. 8 volt, I have 100 ohms in series. The LM version has a 100 ohm internally, so I use only 50 ohm here, or 47 ohm. And then we have 100 in the other IC, the YAESU have here 50 ohms, so I use 100 ohm as in the original circuit in the FT221. This input can be shorted, 3 and 5. Here is a DC bias generated. It can be also fed to this transistor, and we can also short out the output with DC. In the original circuit we have here a transformer, so we have a DC short. So this transistor, the collector, is connected to 1, and also this part is connected to 1. This is fully symmetrical. This is only good for DC checking, not more. I do not check the HF parameters, only the DC ones. And this is done on this test board by the arrangement of the pins. Always this row here is connected, and this row is connected, and so on. And when I arrange the pins accordingly, I have here the pin 8, which gets the 8 volt, or I will increase it to 12 or 15 volt. And here we have the 2 pins connected, 1 and 7. Is it 1 and 7? Sorry, I have to look for it. Yes, 1 and 7. This is not connected to the next row, and here we have the connection of 3 and 5 of the input, and here we have pin 4, which is grounded. And all 4 are arranged in the same manner, so we have the DC supply. And when we can see it here when I connect the 8 volt, and I have 8 volt set. You can see it, yes, now it's okay, it's 8 volt, and the voltage drop across the resistor is a little bit, it's 7.6, and here in the output we have 7.3. The original schematic says 7.4. It's the same. Here we have the input ones, 1.49. We have here 1.5 volt. That's also okay. And this is ground. There's obviously nothing. And we always have the same. You can say 7.55. 7.55, 7.55. Here we have 7.1, 7.09, 7.26, and in the output and input we have 1.4, 1.55, 1.47, 1.45, and 1.49. So I can say in the moment these circuits are regarding DC bias okay. And now I will check it with a little bit higher voltage. Nominal is 20 volt, maximum supply voltage I will go up to 15 volt, just to see whether they are stable even at higher voltages. Here we have 13.8 in the output, 13.5, 13.5, 13.5 in the input, 1.55, 1.49, 1.5 and 1.5. Okay, and now I let this run with this configuration, with this voltage overnight, and check it tomorrow whether it is still okay or whether some of these ICs have a problem. My experience is that also semiconductors, when they haven't been used for many years, for decades, may work in the first moment, and later when they see voltage over a longer time, over hours, days, then they fail. I want to exclude this. When I repair the 221, the FT221, I don't want to have an integrated circuit in it which will fail after some hours again. I don't want to have another Groundhog Day. The new 703s are running since several days. Just for reference, I added the old one, which I took out from the circuit, which is faulty, obviously faulty, and see what I can measure. Input voltage, okay, we have here 15 volt. Behind the resistor we have 13.8. and the open collector output 13.1, and the bias voltage is 1.447. This one has 5.4, here we have 4.7, and so on. This integrated circuit which I took out, which I assumed which is faulty, is not faulty. I don't know what's going on there. It's a bad question mark. Not bad. When we check the voltages again, here we have 13.1, 13.7, sorry, 13.3, 13.3, 13.6, so 13.1 is okay. And most important is this voltage, 1.45. This is two times the base emitter voltage we are measuring here on 3 and 5 to ground, and this is 2 times 0.6, 0.7 volts in series. So this circuit is okay. This 703 is not bad, as I see. I'm surprised. I have question marks in my eyes. So we have to look for the problem anywhere else, but not in this IC. Maybe I've overseen something. When I removed this IC, then I also disconnected this transformer. Pin 7 and pin 1 is then not connected. This is here. We see this output is pin 7 and pin 1. And when the IC is removed, soldered out, then this primary side of the transformer is not connected. And if there is a possible an isolation problem between primary and secondary side, then we would have here a short to ground, because here we have a grounding on this side, and then we would have here a high load to ground. This would also drop the voltage on pin 8. So next step is to check the isolation of this transformer. The transformer is now open because we have here pin 7 and pin 1 not connected, so this is isolated. Only the capacitor is connected to ground. Okay, when there's an isolation problem we will see it also. So I will apply here a voltage of 8 volt to this primary side and see whether we have a short to ground. Okay, this is the transformer. Here we have the two primary sides connected to pin 7 and pin 1. And this is the secondary side which is connected to ground. And here we have a short to ground. You see, dot 18 volt. The current is limited in my power supply to some 100 milliamps. Interesting, interesting, interesting. There's a test point. This one. It also has a short to ground. That is TP303, this one. Something is connecting to ground. Is it this capacitor? But I think it's a ceramic cap. And ceramic cap shouldn't have a connection to ground. Can't be. I have to solder it out. When I switch over to ohm measurement, I'm in the ohm range now. Same result. 0 dot something ohms. On the other side, the primary also 0.5 ohms. And this is this cap 10 nanofarad. Yes, 10 nanofarad. I will take it out. This cap is out, but as I see, it is okay. When I connect to ground, I still have the problem. Zero to ground, or 0.3 ohms to ground on both sides. What is going on there? The only thing which I have is this transformer. Do we have a problem? Is there a contact to ground in this transformer? Crazy. Before I bring back this capacitor into the circuit, I checked it. It is 11 nanofarad, quality factor of 66. So this capacitor is okay. I've unsoldered the primary side of this transformer. Now we have no short to ground. Test point is now open, as it should. And when I connect to the primary winding, you see we have 0 ohms to ground, but this is unsoldered, and also on the other side it is unsoldered. We also have 0 ohms to ground. Something is wrong inside this transformer. I have to take it out completely. The transformer is out. Took me nearly an hour to get it out without breaking the wires. Not so easy to unsolder it. But we have a problem. When I connect to the secondary side and I touch the primary side, we have nearly 0 ohms. On the other primary side also 0 ohms. This should not be, because the transformer should have an isolation between primary and secondary side. No DC coupling. There are 3 connections because this is a center tap, and this is a plus and minus. Let's tell the plus and minus phase opposition, and this is a primary. So obviously something is wrong. But what and why? Well, this core is glued and the glue is is dried out. I have no chance to remove the glue without damaging the wires, so it's necessary to rewind it. I found a green and a red one, copper wire, same as I need for here. I will do this job. Not nice, but I don't see any other chains to repair it. No chance to repair it. It's definitely too small, and the glue again dried out. I have to go the hard way. It will take some hours. I estimate 1 or 2 hours to wind it. I have to count in the number of turns. The schematic itself is not so difficult. It's a B-filar winding, so I can do it. And I will start removing. I think this primary winding has to be first removed, and then I can remove the other winding, the secondary winding, which are B-filar wound. The core is unwound. I counted on one side 30 turns. I'm not quite sure because the wire broke several times due to the dried out paint and also glue. It was a little bit painted also, or sealed with some paint. And on the secondary side I have counted 2 times 15 turns. Center is grounded. I have here the new wires, and now the core is in a solvent to remove the old glue and the old paint. Again, it was sealed with paint. I couldn't find any short indication for short, but as I see the wiring is very, very close together with the primary, and I have the feeling that it was sealed with paint, that the paint was not a good idea, because the protective enamel on this wire was, I think it was dissolved a little bit, so the primary and secondary came in contact. Could be, but why it suddenly happened, I don't know. Well, I leave it in for an hour and then I start to rewind it. The first winding is applied, 2 times 15 turns with a center tap, and to see whether the polarity is okay, I measured the first half of the winding from the center tap to one end. It's 8.66 microhenry, as you can see. And when I measure the total inductivity, we have 34. Double number of turns. Now we have 30 turns, and we have, according to the n square law, 4 times inductivity, 34.6. That's okay. And when I measure the second winding alone, we have again 8.6 microhenry. It's a little bit surprising. I have 2 inductivities in series, and it's not 8.6 times 2, it is 34, because these windings are magnetically coupled on this core, so we have the n square law. And this indicates that the polarity is okay. And now I can add the second turn, the primary one. We have here a test setup. This is the input from a signal generator. I've chosen 1 MHz because my small generator only goes up to 1 MHz, and I'm too lazy to switch on my bigger generators. Doesn't matter, it's a wideband transformer. 1 MHz is also good. The operation frequency is 8 MHz. The yellow channel is the input signal, and here we have two signals, blue and purple, or pink. Is it pink? Yes, okay, it's pink. But it is purple on the screen. Okay, it doesn't matter. These are the two output signals related to the center tab. And when we have a look at the scope, where is it? Here is it. We clearly see that's the input signal. The output signal have approximately half the amplitude. This is 1 volt per division. Here we have 500 millivolt per division, but it's very important we have phase opposition. So that's an indication that the transformer is wound correctly and there is no problem with the phase, no phase error or so. So we can use this transformer now. The transformer is in place now. I fixed it only with some drops of this standard glue. It is also good for plastic and others, so I think that any enamel will not be damaged or corroded or so. I brought in place the original 703, which was in. And now we will see whether it is okay now. We check the voltage at the test point, should be 7 volt. So let's check it. The voltmeter is connected to the checkpoint on the other side, and we have 7 volt as it should be. 7.4, okay, not a big deal. And now let's have a look whether it synchronizes. I fear I have to completely realign it. Okay. The alignment voltage oh my god, is it sensitive? It's 3.8 volt, cannot be. .5. I have to realign the coil as we had and the trim cap. First I have to bring in place the shielding. Complete realignment of the PLL unit is necessary. Cannot avoid it. Aha. It's losing synchronism when we switch off or switch between the bands. That is ugly. Not nice. Not nice. Okay, you see, we have to do something. Now we are at the end of part 8 of our video series SOMMERKAMP FT221. The PLL makes trouble and makes trouble and makes trouble. We have seen that the YAESU 703 is not the problem. The problem was a bad isolation in a transformer, in a toroid transformer. I don't really know the reason. I assume it was the glue which was used to fix the core on the board. The same glue makes trouble when fixing, for example, electrolytic capacitors. It's a little bit corrosive, and maybe the enamel was damaged. The enamel from the wires on the toroid was damaged a little bit, and over the years or decades, we can say, the isolation was getting worse and worse, which made trouble here. Okay, I hope it's solved now. I will realign the PLL unit off camera. Makes no sense. I've showed it in one of the last videos about this transceiver, so it's boring to show it. Stay healthy, stay tuned. See you on this channel.